Hello everyone, this is section 4.2, binomial distributions. A binomial experiment has the following conditions. First off, there's only two outcomes, or it can be reduced to a situation where there are only two outcomes, and we'll consider them to be success and failure. Although the success may not often be what we think of as a success in terms of its connotation, as we'll see through example. But there's a fixed number of trials. So we got two outcomes, fixed number of trials. The trials are independent. Whatever happens in the first does not influence what happens in the second trial. And the probability remains the same. For each trial. And the distribution would just be the outcomes and their respective probabilities, just like we did with the discrete distributions in the last section. Some notation to get used to: n is the total number of trials, x we consider to be the number of successes, p the probability of success, q the probability of failure. And notice that since there's just two outcomes, either success or failure, that q, the probability of failure, is 1 minus p, the probability of success. And then here's our fancy formula. And this version here with the n factorial, n minus x factorial over x factorial, that actually is ncx. So that's why in the first formula, we have that the ncx precedes p to the x, which is raised to the q to the n minus x power. So it's probably going to be easier, rather than literally calculating with regards to the formula for combinations, it's going to just be easier to use our calculator to calculate whatever ncx is. Alright, so here we have an example. We got a family who's going to have 3 children, so that means the total number of trials is 3. We want to find the probability of having exactly 2 boys. So we can consider the success being a boy, and we'll say that x is 2. Now the probability p of success is just 1/2, 0.5, and q is 1 minus p. So I'll say 1 minus 0.5, which is also 0.5. And now we can go to our formula. So the probability of 2 successes will be, okay, regarding the combinations formula, there's 3 trials, x is 2, so n is 3, x is 2, and then we have p, which is 0.5, to the x power, x is 2, and q, which is also 0.5, raised to the n minus x. So formally 3 minus 2 are just simply 1. Now here's what I like to do. I like to calculate the combinations separately. So we'll go to the calculator, and we've done this before, recall. For combinations, 3, probability key. So I go over to combination, enter, value of r is 2, and we get 3. So I like to calculate that and write it down, and then do the rest of the computation. Now the keystrokes here, they aren't really elaborate, but here's what I'm going to suggest in terms of the keys. We'll see this in a more general way in the next example. Just enter 3, then enter 0.5. You could hit the X squared key because it's just, I'm sorry, enter times. And then enter 0.5. You could hit the X squared key because it's just being squared, but generally it's going to be raised to a higher power than 2. So I'm going to use the caret key and to square that, and then times the remaining 0.5 and press enter. Okay, so if we follow those keystrokes, 3 times 0.5 squared times 0.5 is 0.375. Okay, so let's move on to something that's not as simple, something a little bit more interesting. This situation, we have a survey where 23% of Americans say they visited a doctor in the last 3 months. We're selecting 10 people at random, and we want the probability exactly 3 have visited the doctor in the past 3 months. Okay, so basically there's 10 trials, there's 10 people. The value of X we consider to be 3. And the probability of success that they visited the doctor is 23%, and you want to change that to a decimal, so 0.23. And that's P, so Q is 1 minus P, so Q is 1 minus 0.23, or 0.77. Okay, so now we have enough, we have all the information needed. Okay, reminding us of the formula, P of X, or P of 3 in this case, is NCX, so 10C3, and the value of P, which is 0.23, raised to the X power, that's 3, and then the value of Q, 0.77, raised to the N minus X, or the 10 minus 3 power, which of course you just simply write 7. Okay, so as I said in the last example, what I like to do is calculate the combinations separately and write it down. So I'll do that, 10, probability key, go to combinations, enter the value of R, 3, really the value of X, right? And that's 120. So I like to write it down. You don't have to. You could jump right to the rest of the calculation. But we've got 120 times the 0.23 raised to the third, and then the 0.77 raised to the seventh. Okay, so here's the keystrokes on the calculator. So we'll enter the 120 and then times, enter the 0.23, raise that to the third power, and then times, enter the 0.77, and raise that to the 7th power, and then press enter. So following those keystrokes, you should get that P of 3 is, or just so you could check it on the calculator, 0.234314,859 is what I got. And you'd round to whatever place value. A lot of times we go to the nearest thousandth, so 3 decimal places, and 0.34. Okay, so going to the next page. We have more of the binomial probability distribution. And here's an example where we're given, instead of the probability like the last example was probability was 23% was a given. This says 1 in 5. So the probability of success here, P, is going to be 1 out of 5 or 0.2. And the characteristic is that 1 in 5 women attended a musical play. And we sample 15 women, so N is 15. And we should get Q here, that's 1 minus P. So 1 minus 0.2, which is 0.8. Okay, so now we want the probability exactly 3. So that means that the value of x is 3 again. So the probability of 3 is going to be, okay, the total was 15, n, choose 3, and we've got the value of p, 0.2, raised to the x, which is 3, and then the value of q, 0.8, raised to the n minus x, so 15 minus 3, or 12. So p of 3 is equal to, and then I'm going to do the 15, choose 3 separately again, and I get 455, and that's times 0.2 to the third, times 0.8 to the 12th. Okay, so you know the keystrokes from the last example. So just follow along with that. And we have 455 times 0.2 raised to the third times 0.8 raised to the 12th. And that goes to the nearest thousandth, 0.250. Okay, then it says the probability of less than 3. So the probability of less than 3 means the probability of 2 plus the probability of 1, but don't forget the probability of 0 as well. So now we have to do the formula basically 3 times and then add those probabilities together. So the probability of 2 is going to be 15 C2 times 0.2 to the second, and then times 0.8 to the 15 minus 2, which is 15C2 is 105, and then times 0.2 to the second, times 0.8 to the 13th, and that's approximately 23089, so 0.231 I'll say. Okay, so then we have to do it for 1. P of 1 would be 15 choose 1 times 0.2 to the first times 0.8 to the 15 minus 1. 15 choose 1 is just 15. Let me double check that. Yep. So 15, and then times 0.2 to the first, or just 0.2, and then times 0.8 to the 14th. And so we get 0.1319, which I'll just round to 132. Alright, then almost finally, probability of 0. 15, choose 0. 0.2 to the 0. 0.8 to the 15 minus 0. Okay, 15 choose 0 is 1. And that would be times 0.2 to the 0. That's also actually 1, but if you want to leave it in there, that's fine. And 0.8 to the 15th. And we get 0.035. And we'll leave it at that. So, probability of less than 3. Probability of 2 was 0.231. Just add them up. Plus 0.132. And then plus 0.035. 0.231 plus 0.132 plus 0.035. And that's 398. Okay, so then the probability of at least 3. A lot of times we'll set you up for a question like this. At least 3 would mean 3, 4, 5, 6, 7, 8, 9, all the way to 15. So we wouldn't really expect you to do it a dozen times, right? So fortunately, the probability of at least 3, which means 3, 4, 5, etc., is actually 1 minus the probability of less than 3. Because if we take away the probability of 2, 1, and 0, then the total of 1, from the total of 1, then the probability of 3 through 15 remains. So the probability of at least 3 in this part is just 1 minus the result that we just found, 0.398, which gives us 0.602. So a lot of times we set you up that way, where the previous part leads you to solving that final part by taking the complement. Alright, and then mean variance and standard deviation. Couldn't really be much easier here. Just be careful, sometimes a percentage is given, sometimes like the last example, 1 out of 5, or 7 out of 10, whatever. You have to calculate P, but this tells us that P is 0.75. I'll grab Q right away. 1 minus P, so 1 minus 0.75, or 0.25. And here's our formulas for mean variance and standard deviation. Only other thing we need is the value of n, and n is equal to, there's a sample of 180 nursing students, so 180. So therefore the mean, okay, mu is just given to be n times p, so 180 times the 0.75, so that gives us a mean of 135. Variance, always easiest just to find the variance and then square root for standard deviation. So sigma squared is npq. You could actually just take the result of the mean and multiply it by q to get this variance. But if you want to show it literally, 180 times p, which is 0.75, times q, which is 0.25. So our variance here crunches down to be 33.75, and then our standard deviation. And again, that's just the square root of the variance. And when you do this, you want to retain as many decimals as possible so that you don't lose accuracy. Like if you rounded to 34 and then took the square root, you're probably going to lose some accuracy. So you want to include as much as you can of the variance, and you take the square root of that. And that comes out to 5.809475,019, but I'll just choose to round it to the nearest hundredth, so 5.81. Okay, so that's the end of 4.2, which ends the material for exam 2. So we'll see you when you're ready for chapter 5.